Hi, my name is Bruno. I'm a PhD student at University of Minas, Brazil. And I'm a contributor to the LLVM project. I started the MIPS backend there, and I also maintain it. And I'll just start talking about what's LLVM is. Then I'll go a little bit deeper into LLVM design, how it was designed. Then going through the backend to explain how stuff is done in the backend. Then I'll start a little discussion about why using LLVM. It's a good option, especially for embedded systems. Who is using LLVM now, and I'll stop there. Okay, what's LLVM? LLVM is an acronym for low-level virtual machine. It's a compiler infrastructure, and it's also the name from the virtual instruction set. So it's we have a compiler named LLVM. We have an IR from this compiler, which is also called LLVM. The virtual instruction set, it's a low-level representation with high-level type information. What we have here is every IR in compilers with the low-level representation can get compact representation, and we can also get we can also apply a lot of non-optimizations. And with high-level type information, we are able to do like link time optimizations and stuff like that. We also use free address code-like representation, and it's risk-based, language independent, and it's formed when encountering SSA information, which is an acronym for single state assignment, which is a representation where every variable has only one definition. And in this kind of representation, it's a lot easier to apply a lot of optimizations. And on this representation of this IR, we call it bit code. It's like a bytecode we have in virtual machines. Okay, so here's it's an example of the virtual instruction set. After we get a C function like this and pass it through a front end, we get something like this. And so, as you can see, we have like the three address code representation there for a simple add. We get we have infinite registers, so you just return the value, and that's just to show you how does it looks like for now. Okay, now about talking about the compiler, the infrastructure. We have the compiler front end from LLVM. We have two options. We can use LLVM GCC and Clang. I'll talk about these two in the next slides. We also have the IR and tools to handle it. It's the bytecode stuff I said. When you dump it to the disk, we have a lot of tools to manipulate it, and then we can choose to do JIT with it, like in the virtual machine, or call other tools to use the static backends. Okay, the LLVM GCC, it's based on this. It's a hack done in the GCC front end. Instead of using Gimple, we just we convert generic directly to LLVM. And there wasn't a way we can. We also tried in the past to integrate the two projects, but it's not likely. The GCC community didn't like it. I think about because of license. So what we did is we didn't hack, and we removed all the Gimple stuff and below, and just leave we just did the transformation between generic to LLVM. So when you execute LLVM GCC, we after generic, we have LLVM, and LLVM is directly jumped to the disk in the form of bytecodes, or bitcodes as we use. So it's good for us because GCC has very mature front ends like Java, Ada, Fortran, C, C++, and Objective-C. And this is an example of using LLVM GCC. Where we can emit directly LLVM bytecode or use the driver from GCC to call all the tools behind and get the final native code too. But here it's a simple example of emitting the LLVM bytecode, and then after using the LLVM tools to play a little bit with the bytecode. So here we get a bytecode from the C function. Then you can extract just a function from the bytecode and then disassemble it to the LLVM assembly equivalent form. So we have a function here to example, just to show what I'm trying to say. If we want to generate code for another targets, we still have to generate a cross compiler with when we are generating the cross compiler, the build system is capable of gathering information from the LLVM backends and building stuff with the right types, so we can use the cross compiler after. Okay, the other front end we have now, it's called Clang. Clang is it's been worked as mostly as a C front end, but they have plans to C++ and Objective-C. We still we support a little bit of C++ and a little bit of Objective-C right now, but it's the C front end is not stable enough, so the others aren't too. It's still under heavy development process, but it provides better diagnostics. You can integrate it with IDEs, and the one good thing is that in the future, using it, we have no need to generate a cross compiler, because when using the front end, it can gather the libraries from the backend and automatically infer the types that are target specific and generate bytecodes that can suit perfectly to the architecture you want to emit code. And there's also a static analyzer which uses Clang. It's just being used to find a lot of bugs in several projects. Nowadays, there are FreeBSD systems that are entirely compiled with Clang and running. So here's an example of just a warning message emitted by Clang, and in the first box, and in the second box we have an example of Clang emitting LLVM bytecode, passing through the LLVM assembler, pass through optimizations in the bytecodes, and disassembling it again. It's just to show how to use the front end. I'll explain a little bit more of these tools. Okay, LLVM, it's an optimization-oriented compiler. We say that because it provides optimizations for compile time, link time, and run time. Compile time is it's like we know in GCC. It's done like it just driven the options with O1, O2, O3. It maps all the optimizations it has in LLVM to the optimizations GCC has. Link time, because we have LTO in LLVM already. We can just link a lot of object files, removing unnecessary functions and variables. So we can have optimizations for code size. And runtime, because we can have profile-guided transformations collected by a dynamic profiler. This can be done in runtime, because when we are executing, we can